Hello, welcome back. Uh, we're going to continue our course today on paper recycling and science and technology. Again, my name is Richard Venditti, and I'm going to be talking to you today about image analysis used to count ink particles. And we're just going to have a very basic introductory level discussion for this session. Okay. What we're going to be talking about is automated image analysis. And so what we're going to be doing is showing you the steps that are used for a computer to recognize a piece of dirt, much like a human might have. And what we'll find out is that the computer is very talented in the way that it can duplicate tasks that are told for it to do. But it's also, the computer is also, in a way, dumb in the sense that it will only do what we say it wants to do, and it can get confused or tricked very easily. So let's get started. In the past, how has dirt been measured in paper? Well, typically it was done manually, and operators would visually inspect the paper, and what they would be looking for, and here I have an example of paper, and I've got some big dirt spots there, but we'd have these dirt spots in the paper, and the inspector would look at the paper. And what the inspector would do is they would have a standard dirt chart printed by Tappy, and they would compare the dirt on the paper to the dirt on the standard dirt chart, and they would try to match dirt specks on the paper with dirt specks on the standard dirt chart. And what would happen would be that they would count up all the specks of certain sizes that match the standard dirt chart and tabulate them all up, and then calculate the total area covered by dirt. And then the other thing that the operator would know would be how much paper they looked at. So they'd have an idea of the total area that they scanned or looked at. So what they'll do is they'll report a dirt count, and it's based on parts per million, ppm, parts per million. And the parts per million, it's like a percent, but instead of percent where we multiply by 100, we're going to multiply by 10 to the 6th power. That's 1 million. So it's 1 million times the area covered by dirt divided by the area that we analyze. So it's a fraction of area covered by dirt that we analyze. And it's usually a small fraction, and that's why we multiply it by 1 million. Rather than talk about numbers like 0.00047, we can multiply by 1 million and just talk about parts per million, understanding that the number that we are talking about has been, that fraction has been multiplied by 1 million. Let me just show you on the dirt, on our document machine, what a standard dirt chart might look like. Here we have the dots that are carefully printed, and we have the area next to it in millimeters squared. So we've got 5 millimeter squared dot, and then they go down and smaller, smaller, and smaller. One of the things that we notice here is that we're starting down here 0.25, and I know that what you can see here is a function of many things, including the zoom that I've got on here and everything, but still, actually, if you start going down, you're getting to small dots, and you can almost see this 0.04 dot right here. Just barely see it. And actually, that is the threshold, or the border between what Tappy wanted us historically to to count as dirt. So anything above 0.04, the operator was instructed to count that as an area and count that as dirt. Anything below 0.04, for instance 0.03 or 0.02 or less, it would be ignored and basically considered so small that it wasn't offensive to most human beings, that you wouldn't see it at unless you're really, really, really inspecting the paper. So 0.04 was always the borderline. between what Tappy considered dirt and what was too small for Tappy to consider dirt. So that was the tedious manual method to detect dirt. And people did that for a long time, and we can think about the weaknesses of that method. For instance, operator A versus operator B. Each operator might have a completely different eyesight, and one might detect spots that the other one doesn't. It just wasn't very consistent. Even within an operator, the operator starts his shift, starts doing a pretty good job in detecting dirt, but after 5 hours or 4 hours or whatever, fatigue sits in, and they just don't see the paper the same way. And so there's another example of how this was not a very consistent method. So what was the solution? Now as computers become are very convenient to use and reliable, we can start to use the computer and with an imaging system to do the counting for us. But we must be very careful to tell the computer exactly what we want, and we also have to check the work. Okay, so what we're going to do is we're going to substitute that human being with a system like this. What it shows here is we've got a flatbed scanner, which is very common for doing image analysis for visible particles. And we've got a computer. The scanner is actually the eyes, and the computer is the brains. And then what we have also is a software program. And in the software program, what we put in there are rules for decision making. So we tell the computer what particles we want to count as dirt. And we also tell the computer how big should those particles be. I mean, how do you calculate the size of them? And then what calculations to do with them. So that's our substitute for the human being. All right, so how does it work? And I'm just going to go through the basics of a very simple method of image analysis, and we'll briefly touch on later sophisticated methods to do it. Image analysis, how does it work? Well, let's just take an image, and I just took a flower here just as an arbitrary image. Well, when you get a digital image, that digital image is composed of an array of smaller areas. Each of these areas is called a pixel. Okay, so we digitize an image into an array of pixels. And the pixel depends on the resolution size of your scanner. So your scanner is 600 dots per inch, for instance. That means that there's 600 pixels across a square with an there's 600 dots in a linear inch. So basically what that converts to is that 600 dots per inch square is equal to a square with edge of about 0.04 millimeters, or an area of about 0.018 millimeters squared. Now that's interesting to notice because 600 dots per inch is a common resolution for a scanner. Many scanners are better than that now, but 0.018 millimeters squared is less than the 0.04 millimeter squared that was used in the manual Tappy dirt counting. So what we can see is with 600 dots per inch we can get a resolution that can do a relatively good job compared to Tappy. The smallest size a human can detect on an object is about 0.05 millimeters, so in the longest axis. So what you can see is that the 600 dots per inch get us to about the border of human sight, so visible particles. We can get all the visible particles, basically. Now, how does it work? Here, what we've done is I've taken an image. Let's say this is a sheet of paper. And we're going to say that there's an ink particle there, and that ink particle is dark. Okay, so it's dark ink. So what happens is first the computer takes each pixel and it assigns to it what's called a grayscale value. The grayscale values typically run from 0 to 255. And so 255 is perfectly white, 0 is perfectly black, and then we've got all the levels of gray in between there. It's interesting, why go from 0 to 255? Well, it's because of the way computers store data. I believe that's a bit or a byte, but anyway, it's an efficient way to store the data because if you recall, data stored in computers like 2 to the nth power, and that 2 to the nth power is equal to 256, and so this is an efficient way to store it. So that's just a little story about why we go from 0 to 255 commonly. All right, so basically here's our image, and what we notice is that the darker pixels have lower grayscale value. Remember, 0 is black, and so we've got 40, 95, 88, and 20. A couple things you'll notice that are things to keep in mind. The ink particle doesn't always sit 100% on one pixel. So this pixel right here has got a good bit of it has got the dark ink on it, and a good bit of it's got the light white paper on it. So there's always going to be somewhat of that ambiguity where what the pixel is measuring. Okay, so we're not going to have a perfect detection method. However, on average, what this is going to do is it's going to take the particle and make it somewhat smaller, right? Because we can have 100% pixel coverage. That's not going to make it bigger or larger. But we're always on the edges. We're going to have a border of white and black, and that's going to make counting this as a dirt particle maybe more dubious. All right. So what happens next? And we're just talking about very basic image analysis with the computer. The computer will take all those grayscale values of all the pixels, and again, what it's going to do is it'll plot a distribution. Actually, this is just something that occurs naturally. What you see is here we have the grayscale values of the pixels going from 0 to 255, so black to white. And then the number of pixels that are of that grayscale value here, the frequency. And what we see for this ideal case is that we get two peaks. One peak here and another peak here. This first peak is with the darker ones, so this would correspond to ink particles. So we would say that this is area covered by dirt. This peak up here near the 255, or the brighter, the whiter area, are pixels that we want to assign as paper. Okay, so we've got our white pixels are paper, and our black, darker pixels are dirt. Okay, now these two peaks in themselves, what we have to do is kind of separate them, and the simplest way to separate them is just by using what's called a threshold grayscale value. And we can actually input this grayscale value into the computer. We might say, okay, we want it to be 175. In this case right here, it looks like the threshold has been set close to this minimum. And that minimum is going to allow us to separate those peaks in a somewhat effective way. What the computer does next is it takes the image and it says, okay, everything below this grayscale value is going to be dirt, and everything above this grayscale value is going to be clean paper. And that's all it does. And so it gets the area covered by pixels of paper and area covered by pixels of dirt, and then it can calculate a parts per million in the same way that we did it manually historically. Now, the other thing is that I just described to you a manual threshold setting. Another way to do it is to tell the computer that why don't you, as a computer, take the average grayscale value of all the pixels in your system. And basically what that does is it gets an average grayscale value. Dark paper will have a lower average grayscale value, and light paper will have a higher average grayscale value. And what you can tell the computer is, instead of just an absolute threshold that we set, we can tell the computer to take a fraction of the average grayscale value and use that as a moving threshold. This will allow us to compare light and dark paper. For example, you might set that threshold grayscale value at 80% of the average grayscale value. So that 80% will take a fraction of the average grayscale value and use that. And you can see that changes in shade of the base paper will be kind of, will modify the threshold value. And really, I should mention at this point, this threshold is the key critical consideration for defining what dirt is. If we put this threshold too low, we're going to undercount dirt. Too high, we're going to overcount dirt. And it's not really trivial where to put this threshold. In fact, if you look at real paper samples with low concentrations of dirt, this peak is very, very small. And this peak is a little bit sharper. And so we don't really get this nice, neat looking minimum here at all. It's very difficult to figure out where we're going to put that threshold grayscale value. So 80% or some fraction of the average grayscale value is one way to kind of make it an objective rule. But it may also cause us problems. It may not also be the right way to do it. So let's go on. So once the computer has this grayscale value, one way or the other it gets it. Then it goes back to its image. And what it does is any pixels with grayscale value less than the threshold that are adjacent, they're touching each other, the computer will put it as one, put those two together as a size of a dirt speck. And so for instance, if this and this, if the grayscale value threshold was 100, it would put these two pixels together as part of one piece of dirt, and then it will also connect that one and that one later on. So it scans down and it looks for adjacent pixels that are less than the threshold grayscale value, puts them together, and then kind of tabulates it as a dirt speck or ink speck. And finally, at the end, when it sees that there's no more adjacent dark spots, it will calculate an area of that, or a size of that particle. So this automatic image analysis will not only detect the parts per million, but it'll also detect the size of the particles. And I should mention that you can also put in a rule that says, okay, only count for dirt particle sizes greater than 0.04 millimeters or whatever you want. If you want to look at dirt particles that are lower than that, you can even tell the computer to do that. So we've got that thing too, but typically 0.04 millimeters squared is what we'd use just as a default, the most basic. Okay? So the computer scans through all our image, picks out these dirt spots, gets us the areas and the sizes and the size distribution. It's very nice. Okay, so we can kind of do a small exercise here. If this was our sheet of paper and the grayscale value threshold was set to 175, then can we calculate what the parts per million of that sheet of paper are? And I think I'll probably just go to the well, actually, maybe I'll just talk about it. Let's see if I can do this. I'll try the pen. Okay. First of all, we need to determine what the area covered by dirt is. Now we know our threshold grayscale value is 175, so we look and see that only these 4 pixels here have grayscale values less than the threshold. So we know that we have 4 pixels. So the area covered by dirt, we're just going to say it's 4 pixels. Okay? And I'll just try my best here. 4 pixels. So that could correspond to, depending on the resolution of the scanner, to certain millimeters or something like that. But we've got 4 pixels there. And then we can find out what's the area that we analyzed or scanned. Well, we've got an array here. It's 3 by 5. So we analyzed 15 pixels. So the area that we scanned is 15. All right? And then parts per million, all we need to do is remember our equation. So parts per million is actually going to be 10 to the 6th power. Okay, so that's my 10 to the 6th. That's a million. And then it's going to be times 4, which is the dirt area, divided by 15, which is the area we scanned. So that's our fraction that's dirt. Well, if I had a calculator, I could get it right. But let's just say 4 divided by 15 is about 1/3. So basically, the ppm we're getting here is 333, and this is rough estimate, about 1/3 of a million, 333,000 ppm. Okay? So we're getting about 333,000 parts per million for this sheet. And that's just an example, very, very simple way to demonstrate to you what the computer is doing. It's following all these steps. So basically that's what happens with this basic type of image analysis. Now, here are some examples of some other uses. We can count dirt in paper, but we can also count stickies. We can look at stickies in paper, and the way we do that is we might have dark ink and we might have stickies, and stickies typically are either white or they're colored because they've absorbed some of the ink or dirt in the system, and we can dye them blue, and we can either program a computer to tell us how many blue specks are in the sheet of paper, and that will give us our stickies. Or the other thing we can do is we can do image analysis before and after dyeing. Before dyeing, and the assumption here is that the stickies are white and the inks are dark. Before dyeing, we're just measuring the image analysis. We'll measure just the ink, dark ink. And then after dyeing, where the stickies have become dark because they picked up some specific dye, then we're measuring ink and stickies, and the subtraction of the two might give us a measure of the stickies concentration. These images right here were taken on paper machine wires. In the laboratory, where we have a stickies deposition tester, we have the paper machine wire rotating in a stock that has stickies. And depending on the pretreatments of the stickies, those stickies can be either long, slender, and small, or maybe agglomerated and spherical, and we can go ahead and do image analysis on these wires and get a content of the deposits on the wires. I just kind of want to wrap up by talking about some of the other ways that we can count dirt. This was just the basics, just an introduction to just kind of get us to start thinking about how image analysis may operate in on a computer. Now, two things I want to mention. There's one method called the ERIC dirt method. It's called effective residual ink content, and it's used with a lot of dispersible inks that are subvisible. And sometimes we're interested in a newsprint de-inking mill, for instance. We want to know if bleaching is working okay or if de-inking is working okay. What's the cause of some of our low brightness, for instance? So we can go ahead and look at ERIC actually uses a certain wavelength of light that measures these subvisible particles effectively, and can give us a residual content of very small particles. So you'll hear ERIC values used quite a bit. The other thing is that TAPI has developed a new method for dirt counting with a computer automatic system. And basically, it's a little bit more sophisticated than the thresholds technique that I described here. In this case, what's happening is basically, as the computer scans along, it looks at a certain region, and it measures the threshold in that region, the average grayscale value in that region. And then it moves along, and when it sees a big contrast between grayscale values in the major region and then this specific region, there's some complicated computer algorithms, math equations basically. And what it does is it's scanning along, and it's measuring, it's using a different threshold value as it's moving along. And so when it hits an ink particle, it's going to use that area around that ink particle as a way of calculating a threshold, local threshold. And it'll just go through the sheet like that. And so it's a more sophisticated way. It's thresholding at a much higher level. And this is to compensate for changes in brightness and things in the paper going from the X and the Y coordinates and through the paper to different sheets of paper. So if you do go to TAPI standard methods now, there will be a standard method for image analysis vendors to use that will, that code is to be used for measuring dirt, and it's more sophisticated than this. I'm not going to get into it. But there is a standard method that is much more complicated for TAPI dirt measurement with a standard image analysis system, and you'll find that you'll see it in the literature now, and you'll see it in standard methods. And that will conclude, well, before I conclude, let's just kind of wrap up. Image analysis is very important, and what we found out is that computers can basically do a better, they can do a better job than human people can do. In the sense that they can repeat themselves and follow tasks and don't get tired and be more consistent in their measuring. So that's the positive. Now the negative is that the computer is not smart in itself. It can follow tasks, but it can't adapt very easily to strange conditions, and we have to be very careful. We have to do the image analysis, but we need to check the work. And the further thing is when we do input a manual threshold or a relative threshold at 80%, we need to be careful that what we're measuring is truly dirt. It's not just, we're just not misinterpreting what's going on there. The last thing is that there are other more sophisticated methods to measure dirt. I talked about the ERIC method, and then we also said that there's a new TAPI standard method for image analysis with a variable threshold. It's called based on the region in the paper where the scanner is operating. And these are useful and should be looked at when buying a new image analysis system. Finally, more paper is rejected because of dirt than any other specification. So if you think about it, a user gets a sheet of paper, and if there's a visible large ink particle in the paper, that's pretty offensive. And people that are buying the paper will reject the paper because of that. Now, if the color is off by 2 or 3%, it may or may not get rejected. If the tensile strength is off by 2 or 3%, it may or may not get rejected. So you can see that many properties it's very difficult to detect, and they don't get paper doesn't get rejected. But dirt is so obvious and so offensive that dirt is a very important parameter. And so the image analysis that we do to measure the dirt is very important. And for that reason, we have to take very good care in understanding how we're measuring the dirt. And we want to know the procedures and the samples and how to prepare the samples to measure the dirt. And there should be a agreement between the seller of paper and the buyer of paper how we're going to measure dirt, and some checks so that the buyer is confident that the seller is doing it the same way, and that when things are specified, they're specified in an understandable way that everyone agrees upon. So very important. And I think that will finally conclude our talk on image analysis.